Amdahl's law, also known as Amdahl's argument, is used to find the maximum expected improvement to an overall system when only part of the system is improved. It is often used in parallel computing to predict the theoretical maximum speedup using multiple processors. The law is named after computer architect Gene Amdahl, and was presented at the AFIPS Spring Joint Computer Conference in 1967. The speedup of a program using multiple processors in parallel computing is limited by the time needed for the sequential fraction of the program. For example, if a program needs 20 hours using a single processor core, and a particular portion of the program which takes 1 hour to execute cannot be parallelized, while the remaining 19 hours of execution time can be parallelized, then regardless of how many processors are devoted to a parallelized execution of this program, the minimum execution time cannot be less than that critical 1 hour. Hence the speedup is limited to at most 20 Definition: given the number of threads of execution, the fraction of the algorithm that is strictly serial, the time an algorithm takes to finish when being executed on thread S of execution corresponds to. Therefore, the theoretical speedup that can be had by executing a given algorithm on a system capable of executing threads of execution is. Description: Amdahl's law is a model for the relationship between the expected speedup of parallelized implementations of an algorithm relative to the serial algorithm, under the assumption that the problem size remains the same when parallelized. For example, if for a given problem size a parallelized implementation of an algorithm can run 12% of the algorithm's operations arbitrarily quickly, Amdahl's law states that the maximum speedup of the parallelized version is 1/(0.12 equals 1.136 times as fast as the non-parallelized implementation. More technically, the law is concerned with the speedup achievable from an improvement to a computation that affects a proportion p of that computation where the improvement has a speedup of s. Amdahl's law states that the overall speedup of applying the improvement will be. To see how this formula was derived, assume that the running time of the old computation was 1, for some unit of time. The running time of the new computation will be the length of time the unimproved fraction takes, plus the length of time the improved fraction takes. The length of time for the improved part of the computation is the length of the improved part's former running time divided by the speedup, making the length of time of the improved part ps. The final speedup is computed by dividing the old running time by the new running time, which is what the above formula does. Here's another example. We are given a sequential task which is split into 4 consecutive parts, P1, P2, P3 and P4 with the percentages of runtime being 11%, 18%, 23% and 48% respectively. Then we are told that P1 is not sped up, so S1 equals 1, while P2 is sped up 5, P3 is sped up 20, and P4 is sped up 1.6. By using the formula P1 per second 1 plus P2 per second 2 plus P3 per second 3 plus P4 per second 4, we find the new sequential running time is, or a little less than 1/2 the original running time. Using the formula 1, the overall speed boost is 1/0.4575 equals 2.186, or a little more than double the original speed. Notice how the 20 and 5 speedup don't have much effect on the overall speed when P1 is not sped up, and P4 is sped up only 1.6 times. Parallelization: in the case of parallelization, Amdahl's law states that if P is the proportion of a program that can be made parallel, and is the proportion that cannot be parallelized, then the maximum speedup that can be achieved by using n processors is. In the limit, as n tends to infinity, the maximum speedup tends to 1/. In practice, performance-to-price ratio falls rapidly as n is increased once there is even a small component of. As an example, if P is 90%, then is 10%, and the problem can be sped up by a maximum of a factor of 10, no matter how large the value of n used. For this reason, parallel computing is only useful for either small numbers of processors, or problems with very high values of P, so-called embarrassingly parallel problems. A great part of the craft of parallel programming consists of attempting to reduce the component to the smallest possible value. P can be estimated by using the measured speedup on a specific number of processors using P estimated in this way can then be used in Amdahl's law to predict speedup for a different number of processors. Relation to law of diminishing returns. Amdahl's law is often conflated with the law of diminishing returns, whereas only a special case of applying Amdahl's law demonstrates law of diminishing returns. If one picks optimally what to improve, then one will see monotonically decreasing improvements as one improves. If, however, one picks non-optimally, after improving a suboptimal component and moving on to improve a more optimal component, one can see an increase in return. Note that it is often rational to improve a system in an order that is non-optimal in this sense, given that some improvements are more difficult or consuming of development time than others. Amdahl's law does represent the law of diminishing returns if you are considering what sort of return you get by adding more processors to a machine. If you are running a fixed-sized computation that will use all available processors to their capacity. Each new processor you add to the system will add less usable power than the previous one. Each time you double the number of processors, the speed-up ratio will diminish, as the total throughput heads toward the limit of. This analysis neglects other potential bottlenecks such as memory bandwidth and I/O bandwidth, if they do not scale with the number of processors. However, taking into account such bottlenecks would tend to further demonstrate the diminishing returns of only adding processors. Speedup in a sequential program. The maximum speedup in an improved sequential program, where some part was sped up times, is limited by inequality. Where is the fraction of time spent in the part that was not improved? For example, if part B is made 5 times faster, and, then. If part A is made to run twice as fast, and, then. Therefore, making A twice as fast is better than making B 5 times faster. The percentage improvement in speed can be calculated as improving part A by a factor of 2 will increase overall program speed by a factor of 1.6, which makes it 37.5% faster than the original computation. However, improving part B by a factor of 5, which presumably requires more effort, will only achieve an overall speed-up factor of 1.25, which makes it 20% faster. See also, Gustafson's law, Kappa-Euro-flat metric, Moore's law, notes. References: Rogers, David P. Improvements in Multiprocessor System Design. ACM's SIGARC Computer Architecture News Archive 13, 225 231 doi, 10.1145/327070.3272215. ISBN A0-8186-0634-7. ISNA 0163-5964. Further reading, Amdahl, Gene M. Validity of the Single Processor Approach to Achieving Large-Scale Computing Capabilities. AFIPS Conference Proceedings, 483 485 doi, 10.1145/1465482.1465560. External links, Cases where Amdahl's law is inapplicable, Oral History Interview with Gene M. Amdahl, Charles Babbage Institute, University of Minnesota. Amdahl discusses his graduate work at the University of Wisconsin and his design of WISC. Discusses his role in the design of several computers for IBM including the Stretch, IBM 701, and IBM 704. He discusses his work with Nathaniel Rochester and IBM's management of the design process. Mentions work with Ramo Wooldridge, Aeronautonic, and Computer Sciences Corporation, re-evaluating Amdahl's law, A Simple Interactive Amdahl's Law Calculator, Amdahl's Law by Joel F. Klein, Wolfram Demonstrations Project, 2007. Amdahl's Law in the Multi-Core Era, blog post, What the Dollar At? Is Parallelism, Anyhow? Amdahl's Law applied to OS system calls on multi-core CPU.